Hello everyone, how's everybody doing? I hope you're all safe. Announce yourself safe on, Facebook. Again, one more time, I got to skip what I was supposed to be doing here because I had lots of questions come in and I want to address those questions, okay? First of all, I want to remind everyone we have a conference, and I don't know how this coronavirus is going to affect that. That's going to be pretty interesting. I don't know. We got to find out and see if they close all the airports if we keep going like this, you know. Okay, and then the other thing, I want to remind everyone that I've uploaded a book, okay, and you can download it. It's for free, and it talks about the rope hypothesis, brings you up to speed on what this channel is about, okay. If you have a second language, please contact us at tokakaka@hotmail.com and help us out translating it into some other language. Okay, so all contributions are accepted. Okay, for any language. I'm translating it into Spanish right now. I'm still in the process. Probably won't be out until April, I suspect. Anyways, let's get on with it. I want to address a lot of the issues that were raised, questions, objections, criticism, comments, etc. Okay. Here's the first one. The first couple were pretty nasty. One person says, okay, I've had it. I had my fill. Unsubscribing. Okay, and this comes at the heels a couple months ago. A fractal woman said, boycott Bill. So from now on, it's my new name. I'm Boycott Bill. Okay. So now you know. Okay, and this site has the knack of weeding out the riffraff. So if what you do is any of the following that you see there, if you do observations or you bring those subjects up as defenses or attacks, or as a defense of quantum mechanics or mathematical physics or your interpretation of science, if you bring any of these up, well, you're in the wrong site. What you're doing is religion, okay? And that includes observations, experiments, predictions, any mathematics, whether you use equations, calculations, you do measurements, or you bring measurements like they're important, particles. Especially, we attack particles. Anyone bringing the ether, which is a synonym of particles. A lot of people who are etherists are not aware of that. Waves, we have no use for waves. Waves is a concept. We don't move concepts around in physics. No evidence or proof. That's for convincing the jury. We don't try to convince, we try to explain. If you use any of those words, mass, field, charge, time, force, especially that one at the end called energy, any of those belong to religion. None of those belong to science. If you talk about Popperian falsification, you bring in space-time, black holes, dark matter, if you move concepts around, and if you do descriptions rather than explanations, well, then you're in the wrong site, okay? This is what we do here. We do science. What is science? Rational explanations. And it's divided into physics and philosophy. Here we do physics, and the golden principle of physics is that it requires an object. You cannot do physics without an object. What is an object? That which has shape, and that's the first word that any person has to define when he does physics. He has to know what an object is, because you can't do physics without an object. And I like to say that the scientific definition of the word object destroys all religions, okay? So why? Because people have to choose whether they're going to move objects or concepts. And is space-time an object? Well, if it has shape, you better be able to draw it. If you can't draw it, then you got a problem, because then it's not an object and your whole theory goes down the drain, your whole explanation, your physical interpretation, okay? Here's another gentleman. He reserved some choice words for me. I won't mention a lot of the things that he said, but he said, your wordplay is BS. Produce the holographic fractal nature with ropes. Produce something practical. Well, this gentleman obviously is divorced from physics and from science. He doesn't know what physics or science is. No, sorry, in science we do not use just undefined words. We do not play around with concepts especially. We have to define our terms, and if we're going to claim that something is an object, we better be able to draw it. And if we, on the other hand, introduce a concept that makes or breaks our theory, you had better define it, okay? And fractals, no, mathematics is not a part of science, sorry. Science is about explaining and math is about describing. Math can only describe. Produce something practical? No, technology has nothing to do with science again. You know, science is about explaining and technology is about developing gadgets through trial and error. So we do not do math, we do not do technology, not in science. We do not do experiments, we explain them. Our lab tech, the boy, the gopher, he does the experiment. The scientist, the guy who explains what happened. Okay, so there's a difference between doing and explaining. Okay, so we don't do experiments in science. You can do all the experiments you want in your basement, right? In dark basement. When you come to the conference, we want you to explain, you know, if you did gravity, if you did magnetism, we want you to explain the mechanism. That's what we want to hear, you know, or see. Okay, one gentleman put in there, he says, light travels, let me wait in this here. Says light travels longitudinally and appears transverse only when it encounters matter. It's a ray, it's a line. No such object as ray, no such object as line, not in physics, okay? And also no such object as a beam, just in case, right? Physics demands objects. You can't do physics without an object. An object is that which has shape. Ray, line, and beam are concepts. Line, the real line, you know, the one of geometry, is a physical object, but it's a two-dimensional elongated square or rectangle, right? That's what a line is. For example, the line that comes right after the word object there at the bottom, that's a line. Why? Because it's two-dimensional. It has width and height. Okay, 2 dimensions. If that's what you talk about a line, well, I don't know what that has to do with light or how you can simulate light with that line. If that's not the line you were talking about, you were talking maybe about an itinerary maybe, or maybe you were talking about or thinking about trajectory, you know, and you put a line there to represent it pictorially. Well, we don't care about that. That's you're using objects to represent concepts. You're using the dot to represent location. You're using the heart to represent love. That's what you're doing. Okay, so keep in mind what the context is in all this, right? You have to look at the context. Okay, here's another gentleman, and he said the end and the aim of all sciences is description. The simplest possible description of the given observed of nature. Merely the relation of actual to actual is valuable, and this is exhausted by description. The demand for description of the actual stands in certain opposition to the demand for explanation. And he apparently brings this quote from Ernst Mach, who was primarily a 19th century researcher. Okay? And it turns out that, I've always put this comment from Donald Simonek. He's a professor emeritus at university. And he says science doesn't explain. Science describes. Okay? Now, whether he understood what he said there, I don't know. But the point is that the reason all these people talk about description is because that's all that math can do. Math can only describe. An equation is only a description. There's no explanation. You can't say that, when you put an equation, E equals mc squared, for example, or force equal mass times acceleration, or any equation. You have not explained anything. All you've done is described some kind of motion there. Okay, that's all you've done. And so, no, math, of course, it was predictable, right? In retrospect, if you were in the 17th century and you had these new researchers, people like Galileo and Newton come on board, they took a tangent and took science, so-called science, natural philosophy, as it was called. They took it in a separate path. They just kept developing along mathematical and experimental lines, and they forgot about explanations. And today we have mathematics developed to ridiculous levels, equations that we don't even need, and we have no explanation, no rational explanations for how this universe works. We don't know, in other words, from the universities, right? We have no idea how a magnet attracts another. We have no idea, what gravity is, how light works, how it does its magic, and all the explanations you'll find out there are all irrational, completely irrational. Primarily because they're in the business of moving concepts, okay? That's why. And here you have it. This is the difference between an explanation and a description. Explanation is the causes and reasons in the case of philosophy, but the causes in the case of physics, and it's a mechanism. Okay, you're trying to explain a mechanism. You're giving a physical interpretation of some, especially invisible phenomenon. Something you observed or did not observe, because you can't observe the mechanism of light. You cannot observe the mediator of light or of gravity or of magnetism. And so you have to explain how that mechanism works. That's what science is about. That's what physics, as it relates to physics, right? That's what it's about. What is a description? Just a listing of properties of an object. So we don't just list and say, a table has 4 legs and one top, right? One surface. Is that I did science because of that? Or, I let go of the pen 10 times. Repeatable experiment, right? And it always falls to the floor. And so I go to the conference and I say, yes, I performed an experiment. It's repeatable. You can all repeat it in your own dark basements. And what I did was let go of the pen and it fell to the floor at 9.8 meters per second square. Measured exactly. That's science. You let go of a pen 10 times and you measured, and you bring a calculation, and that's science. No, science is trying to tell me how it is that pen fell to the floor. That's where physics vibrates, okay? But telling me that you described something because you did it 10 times or 1,000 gives us no insight into how this universe works. And that's why that's not science. And especially this gentleman continues. He says, the fellow who said that science is about descriptions, or put that comment from Ernst Mach, right? He says also the most prolific case of movement in the universe is movement under gravity, okay? And in that, there is no contact between objects. Maybe, okay? When observing the universe, it is apparent that objects move without contact with objects. Oh, is it? Example, magnetism, electromagnetism, static electricity, gravity. What this gentleman is proposing is that we do physics without objects. That's essentially his attack, his angle, right? He says, we don't need objects because I don't see any objects when I do gravity or when I do magnetism. I don't see any objects. And so what's this nonsense about bringing objects in to fill in the blanks of invisible phenomena, right? Yeah, if you don't put an object there, if you don't put an object between the floor and the pen when you let go of the pen and it falls to the floor, then you're explaining with spirits. You're using black magic. You're saying that the pen fell to the floor and there was nothing in contact with a pen, with the skin of the pen. And yeah, 90% of the people in the world are religious, including all the mathematical physicists, because they do explanations with concepts. You know, they have no problem moving concepts around, and that's even worse than traditional religions that put spirits and angels and God in there. You know, I can at least imagine an angel, but I cannot imagine four-dimensional space-time. So we have an issue where these people are doing so-called physics with non-objects, and they call it doing physics. No, you're doing religion. That's what you're doing. And I'm sorry it offends your religion, but yeah, we need a mediator. We need a physical mediator. The reason you can't see or touch that mediator, like gravity or magnetism, is because that's not the definition of the word object. And again, that's why it's so important to define the word object, and that's why the word object destroys all religions. You have to define object, and when you define object as that which has shape, there is no provision for see or for touch or for any other of the senses. So you can't just go in there and say, well, I can't touch the mediator of gravity. I can't see it. Yeah, because that's not the definition of an object, or of a mediator, which is a synonym. No, the mediator has only one criterion, and that's shape. Not see, not touch. Okay? And that's why you can't see or touch, because you have to begin by defining what an object is. See, if you define it as see, touch, we got a problem, and we've covered that ad nauseum in the past. Okay. Okay, one other gentleman, he asked, what is vacuum? What is vacuum? Well, first of all, it's not a what. Okay, that's the first thing we have to clear up. It's not a what. What is vacuum? Okay, vacuum is a synonym of the word nothing. That's what it is. Nothing and vacuum mean exactly the same thing in physics, not in ordinary speech, not in mathematical physics. I'm talking about rational physics. Vacuum is simply another word for nothing. And then space is another synonym of these two words. Vacuum, nothing, and space mean exactly the same thing. They stand for that which doesn't have shape. That's what nothing is. Something is that which has shape, and they are both antonyms, nothing and something. Now we can use these definitions scientifically, consistently, rationally, right? The whole works. And anyone who disagrees with this or has a different version, okay, all you got to do is just define the words and we're done. That's how easy it is. So you want to know what vacuum is? Define it, and then we'll know what it is. What is vacuum to you? Okay, you got my definitions there. Now you have something to compare them against at least, okay, because now you got a scientific definition in front of you. Okay, another gentleman, he put a comment, quite a few comments in fact. Bill's own drawing of the electromagnetic spectrum and his own statement, he put I guess the reference there, shows that that color is a function of wavelength. We both agree. No, we don't. I agree, but you don't. And here, let me show you how he disagreed. This is what he put a couple of weeks before. He says, Bill claims that when light goes through a dense medium, we should see a change in color. We do not. Please look at the reference below. It shows speed slowing down and no change in color. Okay, so he was saying that you have light going through a medium, and it doesn't change color. And this is when you go to that site and look up the reference there, this is what you get. And he's saying that it doesn't change color. The little piece of light, that photon, he thinks all these are photons that are being filmed. And so one photon hits that blob there, okay, and he says, see, it doesn't change color because he thinks this is for real, okay? And he, of course, he's never going to admit that he was wrong. He thought that this was the real thing, that the bozos at wherever, I think it was Fermilab perhaps, I don't know where they did this now, that they filmed this and that they uploaded the film. No, this is done in Hollywood. This is cartoon, okay, just to make sure that you understand. This is nonsense what you're seeing there, okay? It's a simulation of what they did. So, no, we do not agree. I agree, but you don't, that light does change color when it goes through a denser medium. And it should be so because, first of all, according to the rope model at least, right, you exchange wavelength for frequency, okay? In other words, you have the link length. Here's my little rope. And you can see that, you know, if you untorque it, you get longer link lengths and fewer links. And when you torque it, you get the opposite. You get more links, and each one is shorter. Okay, so that's standard. It's the wave equation. That's why the wave equation of light, right? It can only be simulated with a rope. And this guy was saying that light does not change when it goes through a denser medium, and he put that reference there for that video. Well, yeah, light does change, and you don't need to go to that video. You can just shine light through a prism, and you'll see that the colors out of white light. You introduce white light, and it breaks out into the rainbow colors later on. So yeah, a prism does break up light into different colors. And so to say that the same color remains through the prism, I don't know. And of course, what changes is the wavelength. And that's what everybody in his religion, not in mine, his religion says that it's the wavelength that shrinks as the beam of light hits, for example, glass. So it goes from air to glass, it hits a denser medium, and now what shrunk is the wavelength. And yeah, if the wavelength shrinks, then according to the spectrum, and I showed that the other day, here's the spectrum, okay? According to the spectrum, light had better change colors because wavelength changed, okay? And we're in agreement with the spectrum. We're saying that, you know, when the links become shorter, you know, you're going to have a different color. That's the one on the bottom there, okay? That's the rope model of the spectrum. So we're consistent with that. What's not consistent, we'll find out in a minute, is quantum mechanics. Quantum mechanics has a big trouble with the spectrum. It's not consistent with the spectrum, okay? And here we'll see it in a minute. But anyways, this is what essentially these people are saying. Most people out there, okay? There are different opinions, but this is the main one that quantum supports, and that's the one I've been saying for the last couple times, that you have a long wavelength of light come in, it hits glass, which is that blue part in there. The wavelength shrinks in the direction of travel, it becomes shorter, and therefore color should change inside the glass. And then when it comes out, the wavelength goes back to the same wavelength, right? The same length as it came in. Okay, so this is the standard explanation that quantum mechanics gives. Okay, but this fella insists, and he says, no, look, that's not the case. There's a different explanation for this. Okay, let's see what's the explanation. So he repeats, most people are willing to accept that passing through glass would slow down the light. Okay. But they were puzzled about, he's quoting, by the way, what a fellow from Fermilab is saying. So he's just quoting that, okay? But they were very puzzled about light speeding up when it left the glass. Yeah, good question. Why does light go back to the same frequency and wavelength as it came in? What changed in between? Okay, because now we got to explain why light goes back to little c, to 300,000 kilometers per second. It comes in at 300,000, goes through glass at 200,000, and now it comes back out at 300,000. Okay, that's what we have to explain, and this is what this guy is saying. Okay, he says they were puzzled about light speeding up when it left the glass. Okay. Before light hits the glass, it travels at the speed of light in a vacuum, okay, because air and vacuum are more or less the same. When it passes through the glass, the light causes the electrons to move and generates a second wave that adds to the light. In other words, there is only one wave, not two, Bill, he says, okay? And as you can see, we were talking about two waves. We're talking about light still moves at the speed of light, that's light, okay, in a vacuum, but the waves from the electrons move at a different speed, and the combined wave moves slower than light would if the atoms weren't there. In other words, he's saying, here comes light, right? It's got its own wave. Now it goes into the glass, it shakes the electrons create a wave, there's a vibration of a wave, but electrons move a little slower, okay? And so you have this fast light coming from air, slow wave from electrons, and the combined wave, they somehow mix, okay? They somehow blend, okay? And the entire wave within the glass travels slower, okay? And then when it exits, since the electrons are no longer there, that wave of electrons inside this solid piece of glass, right? Now, when light goes out, it doesn't have that impediment, and so light essentially never slowed down. That's essentially what they're saying. Okay, they're saying comes fast into the glass. Through the glass, it goes slow because it mixes with this other wave that slows it down, that somehow retards it. And then when it comes out, the electrons are not there to slow its speed, and it continues speeding at the same velocity or speed or whatever, right? 300,000 kilometers per second, essentially in air. Well, there are too many problems with this. Okay, so let's look at them. Here's a list, okay? This idiot is a person with big ideas, so we call them idiots, okay? And this idiot, Don Lincoln, okay, who represents Fermilab, he does it on your buck, on your dime. You know, Fermilab is a state-supported institution. This guy works there. He makes money saying this nonsense, and so it's really ridiculous that a guy like this would be working in such an advanced place. That's the first thing I got to say. But he never explains the mechanism, okay, how two waves physically interact. In fact, you can't, because a wave is not a physical entity. So they use this stand-in, this joker, this wave word. They put it in there and say, oh, the waves interact. Well, you know, what is a wave to begin with? But let's continue. Idiot Don Lincoln justifies the return of light to its normal speed when it exits the glass on the fact that there are no more electron waves to slow it down. But it turns out that air also has electrons and electron waves. So it's not like air is not made out of atoms. Is that what he's suggesting? I mean, if he said it goes back to vacuum, we would accept it, but it's going into air. So it does go back into where there are atoms and where there are electrons, okay? Just keep that in mind. But then light should go back to white when it exits the prism and not have rainbow colors. See, because if light enters at a given speed at 300,000, it hits the piece of glass, it travels 200,000 kilometers per second through the glass. When it goes back out to 300,000, then we should not get a rainbow. We should get white light just like it came in. Okay, that's another issue. Idiot Donald Lincoln of Fermilab explains and illustrates that slowing down of light is due to amplitude. And in the religion of quantum mechanics holds that amplitude has no effect on speed. In fact, that's one of the few things they're right about, because there is no provision for there's no provision for amplitude in the speed of light, or for that matter in any wave. Okay, but here it is. Let's show that this is the case. Okay, this is the gentleman, Don Lincoln, Fermilab. And, you know, the important thing here is that, or one of the things you should note, is that he's got all these equations in the background. You know, he comes in there with this board all full of equations, throwing authority at you immediately. You know, the first thing he does, even before he begins speaking, right? So he's got all this stuff in the background. He talks in front. Unfortunately, I don't have, you know, equations behind me. Okay, I have only bottles of rum and beer. And so he says in this video, why does light slow down in water? And he's got almost 560,000 views, 25,000 people who upvoted his video. That tells you how many retarded individuals there are. I mean, you know, these people listen to this fella and they have no clue what he said. And so let's find out what he said. Let's find out if he deserves his job. Okay, or he should be cleaning latrines, you know, at the bus stop with a toothbrush, because maybe that's the only job this guy deserves. Okay, the first problem is, you know, he starts by showing a wave. So what is the wave according to Fermilab? Now, this is a world-class institution, okay? This is an accelerator in Chicago, right? And here it is. This is the famous wave, okay? Look at that. What is that, a string? Is that a little cord? Maybe a chain? I don't know. And he talks about wavelength of this what he calls a standing wave. And what is it? A bunch of vectors. That's what it is. They're going to be moving numbers. Mathematicians, you know, wave numbers, and they call them vectors, and they call this a wave. So what's misleading about this picture already is that he's using this notion of wave. and there is no such thing as a wave. So he's going to talk about waves. He's going to use this abstraction, and he's going to use it as a real entity, when in fact a wave, the so-called wave, Maxwell's wave, is just an abstraction. It's a number. He's got all this wave of numbers. That's what he's got. That's what he's waving. Just be aware of that. Okay, his wave is no good. Let's see, how about his atom? Maybe his atom is a lot better, okay? I always wanted to know what an atom looks like, and who else but Fermilab can tell me what an atom looks like? Okay, here it is. It looks like it's Rutherford and Niels Bohr's planetary model. They have these beads moving along the wires. I guess that's what it is, right? So that's their atom. That's the famous scientific atom. So we've got a wave, which is a little string moving up and down. And just to rub it in, let me show you this one more time. The only reason you can produce a standing wave is because it's got to be tied at both ends. If you're holding one end of that string, the other end had better be tied at the other end. Otherwise, you cannot produce a standing wave, okay? Always when they imitate the standing wave, they tie the other end somewhere or have someone hold it. It's tied at some place, because if, it's got to be held in order to do this, right? But what happens if I let go? Well, I can't produce a standing wave, believe me, but you can try it in your own basement. See if you can produce a standing wave without holding the other end. And then even if you hold the other end, why would it go so neatly? Why would it be so perfectly even, the sine wave that you always see? Why would it be so perfectly even? I challenge you to film your own standing wave. Just tie a string or whatever you want to the wall, right, or to a post, and shake it up and down, and film it from the side. See if you produce very perfect, waves, undulations. Impossible. So they already failed before starting. And as far as the atom is concerned, like I said the other day, this is what they have to do. They have to tell me what holds the electron to the proton if they're going to treat the electron as a little bead. If the electron's going to go out and shake and produce this wave of electrons that's going to interfere with the waves of light, first thing they got to do is draw their atom. And the only issue there is what is the brown stuff? What is that brown stuff that keeps the electron bound to the proton? That's the only thing they have to explain. Okay, it's very simple, really. All you got to do is draw it. And I don't care about Mother Nature's atom. I want their atom, the one that you're going to present. I need to see the mechanism that you're going to present. And so far, they just move on. They say, oh, the electron does this and the electron does that. No. Tell me what keeps the electron tied to the proton to begin with before you go and explain your theory, okay? Okay, so what does Lincoln do? Well, the Don Lincoln, this fellow, what he does is he's going to go in there and he's going to talk about constructive and destructive interference. And he's going to mix this, he's going to confuse this with speed. He's going to talk about for those of you who are familiar with it, you have one wave, if two waves are in phase, then they add up and they make the wall shine with higher intensity. And if they're out of phase, well, they cancel out and there is no intensity. You've probably heard of the slit experiment. That's what happens. All those fringes are waves which are in phase and waves which are out of phase. Light bands or bright bands and dark bands. That's what it is. And this is what this guy is going to introduce. Here it is. And this is all from his site, okay? This is all from Fermilab, a world-class institution, okay? Just so you know. Okay, first he's going to show that waves that are in phase add up, okay? And then he says those that are out of phase, well, they cancel out and you get a straight line. Okay, so far nothing about speed, okay? You can see it again there. They add up, okay? He's talking about amplitude, really. That's what it is. That's what he's showing. There's nothing about speed there. Okay, let's see if it improves anywhere, okay? Here it is again. This is in motion. And again, what you're going to see is amplitudes where they cancel out and where they enhance each other. All he's doing is raising the amplitude of the beam of the wave. He's saying, look, if they coincide, the amplitude at the bottom is higher, and if they don't coincide, well, then the amplitude on the bottom, just vanishes. Essentially, there is no amplitude. So far, we're talking about amplitude. There's nothing about speed in that picture, in that illustration that this fellow Lincoln from Fermilab put in there. And just in case he rubs it in one more time, and he does say it. Let's see if I can get it here. Okay. I think it's this one. Got so many of these sometimes. Here you can see it. That's the electron, okay? And it has that red wave. That's the wave of the electron. The blue one is the light wave. So far, there's nothing about speed. In fact, all he's showing is different amplitudes. So he takes the electron, takes one electron ball, he has it describe this wave, and the waves, they coincide. The only difference between the wave is not speed, it's just the amplitude. That's what he's showing. And that's what he's explaining, in fact. Here it is again. And he goes through this detail, just explaining, what all these are. Here it is. He breaks them apart, okay? And you can see that he's going to take this, okay? He's going to take the wave, the light wave, and he's going to take the electron wave. And what he does is he's going to have simply a difference in amplitude. He's saying the new wave not has a different speed, it has a different amplitude. Amplitude has nothing at all to do with speed, and that's what this bozo from Fermilab, who makes billions of bucks, right, on taxpayers' money, this is what this guy explains in his video on behalf of Fermilab, okay? So this guy should be fired, okay? He's no good. He doesn't even know what he's talking about. And here we have some testimonies, just in case, okay? Let me get back in here. Just so you know what the official version is out there, which disagrees with this bozo from Fermilab, okay? Again, I think he should be fired for saying such ridiculous nonsense that amplitude has something to do with speed. In fact, you can see in the equation down there, that's the wave equation of light. Do you see any provision for wavelength, for amplitude? All you have is frequency and wavelength. That's it. There's no provision for amplitude, which is what this bozo from quantum mechanics Fermilab explains. Okay, but there it says, you can look this up on your own and Google it on the internet. The amplitude of a wave does not affect the speed at which the wave travels. Of course, it doesn't. And this is what this individual from Fermilab essentially illustrated and explained. He did both, okay? Just in case you missed one, you got the other one. And then another site says the wavelength, color, and frequency of the light do not depend on the amplitude. Of course not. They don't. Because amplitude has to do with intensity, not with speed or with color. Okay? And so this fella, Don Lincoln, he should really go to kindergarten physics and learn the basics. Okay, he's talking nonsense, and of course he fools people like this fellow who put the comments. Okay, and if you go on I just pulled one out of the YouTube, and there's one fellow, and this is his site, but there's many of these. I just pulled this guy at random. Okay, and he says, he talks about constructive and destructive interference, where you have all these amplitudes which, interfere with each other. It's got to do with amplitude, not with speed at all. So what this Don Lincoln explained, he doesn't even know where he's standing. That's the reality of it. Okay, let me put this here. Got so many of these. Putting them up here. I showed the other day from the Stack Exchange just to reinforce that the official version has to do with wavelength, okay? That what squashes is the wavelength. The wavelength is not as long. It shrinks it in the direction of travel. That's the official version of quantum. What this guy from Fermilab says has nothing to do. I mean, this fellow who put the comment, he said that my version is antiquated. Well, it's in the Wikipedia, as you can see it there. These guys also from the Stack Exchange. So instead of accusing me, go over there in Wikipedia and change the Wikipedia. Fight with them. Okay, don't tell me. I don't defend quantum mechanics. So if you're going to defend quantum mechanics, at least know or understand what they're saying. Understand your own religion. Right now, you don't understand your own religion. These guys are saying when a beam of light crosses the boundary between two medium, its frequency does not change. Its wavelength changes. Its wavelength changes. This is the official version of quantum. Frequency of light wave does not change from medium to medium, while the speed of light and thus wavelength does. Okay? So it's wavelength that changes according to quantum mechanics. It flattens out when it reaches in there. Now, if it's because of the electron waves getting in the way, I don't care. All I'm saying is what changes is according to quantum, okay? What changes is only the wavelength. Frequency remains the same. And that's how they produce the shortening, the slowing down of light, okay? Because, again, the wave equation says C equals frequency times wavelength. The velocity of light is equal to frequency times wavelength. And what they do is hold frequency constant and shorten the wavelength. That's how they make light go slower. That's their interpretation of why light goes slower through glass or through denser medium. And Wikipedia says the same thing. The refractive index can be seen as the factor by which the speed and the wavelength of the radiation are reduced. Okay? So you want to fight, you're fighting the wrong guy. You got to go into the Wikipedia and change it. Okay? Change the Wikipedia, then we'll know who's antiquated. Okay? Whether it's you or me, okay? Right now it's you, because what you mentioned is one guy that mentions out there that it's got to do with amplitude, and amplitude has nothing to do with speed. So I don't know. If you're going to follow people from Fermilab simply because they put a bunch of equations on the board and say, oh, how much authority, and this guy's a PhD, and yeah, and he represents Fermilab, yeah, you can throw it all into the trash can. This guy doesn't even know who he is, who his mother is, okay? So no. And here we have another issue with that, and that's the energy, okay? See, because what I illustrated the other day is that you have these longer wavelengths at the top and shorter wavelength at the bottom. And in order for frequency to remain the same in both those waves, the one at the top has to make up the difference with speed. That means that wavelengths which are longer, they have to travel faster in order to catch up with shorter wavelengths. And what happens with that? What it means is that when light hits a brick wall, okay, and it flattens out in the direction of travel as shown at the bottom, that means they travel slower. That's the explanation quantum gives, okay? So that's the official version. And, you know, what can I say? We have a problem first because, you know, here, as I showed the other day, when light exits the glass, it's going to encounter first a bunch of atoms from air. You know, those particles there, that's air. And so the question is, why doesn't it flatten out there? Why does it travel essentially at the speed of that light travels in a vacuum? So you got to explain that. I mean, what's different about air from glass? That's what you got to explain. And of course, these people can't do it, much less with the word wave, because wave is not a physical object. And this is the way this Lincoln guy explains. You can see he doesn't illustrate what he's supposed to illustrate. He should be illustrating waves. What he does is he put a little line there. He does it all with lines. And you're supposed to guess what the mechanism is. And you won't. He just says it does so, and you better believe it. He just says that the wave of light interferes with the electric field, in other words, the electrons that are waving inside the glass, and that's what slows it down. But he doesn't show the mechanism. You can't determine the mechanism just by looking at this little drawing that he did there with just lines. You know, he's really got to explain it with waves. I mean, if he's going to put it on YouTube, at least show the mechanism. Just tell me about it and say that it is so, which is essentially what he says. Okay, and here I also illustrated this the other day. Let me get back in here, where I gave an example of the color red. And you can see what's happening according to quantum mechanics, okay? It's important to note that this is from quantum mechanics. I'm just illustrating what they don't, okay? And you have the wave equation, C equals wavelength times frequency. What they do is keep frequency constant always. They never vary or change the frequency. What they do is go in there and shorten the wavelength, okay? So wavelength went from 650 to 433 nanometers inside the glass. Okay, and they say, look, the wavelength change, which means the color changes first. It has to change because the wavelength is a function of color is a function of wavelength. That's first. Second, they say that it changes, and that's why light travels slower, because it's the wave which is shortened. So now because it's shortened, it travels slower through the glass. And then again, why does that wave expand leaving the glass? Well, you can say electrons are no longer there, but that's not true either, because air is made out of atoms and electrons. There should be waves of electrons there. They should be interfering with the passage of light. But even if we concede that, then the light that should come out should be white out of a prism, and that's not the case. It comes out with the colors of the rainbow, as Mr. Newton showed 400 years ago. So quantum fails in all predictions, to use that term, okay? They fail all predictions of a prism. They cannot explain it, and their explanations are all retarded, okay? And here you can see what they should be predicting. In other words, if the incoming white light is broken up by a prism, first you can see that we have a rainbow inside the prism. That's the first issue. And this means that, according to quantum, that what changes the wavelength is what changes in each one of those waves, okay? So red has a different wavelength than blue or violet at the bottom. But then, coming out, now there's no impediment from the electrons, right? There's no atoms there, according to them, or atoms that affect the waves. And so why doesn't white light come out? Okay, we should have the same white light coming into the prism as coming out of the prism, and that's not the case. Okay, what we have is white light leaving. The color of the rainbow leaving the prism. Okay, and so this fellow continues with another comment on that. Let me get back in here. And he says, when you pass white light through a prism at an angle, you get dispersion. Well, thank God he admitted that, because the other day he said the color remains the same. And if there's dispersion, hopefully colors change inside the prism. Okay, that's why when they come out, you see all these rainbow colors. I mean, if nothing changes, then there should be always white light everywhere, through the prism and also, outside the prism. White light separating into its individual colors. Bill, please explain how light stays the same color once it leaves the dense material. Okay, I'll explain it. According to Bill, once the ropes leave the dense medium, the rope length should get shorter. Where he got this, I don't know. This guy wants to put words in my mouth. No, I don't say that, okay? This is his tiny brain that came up with this, and obviously he doesn't have the qualifications to analyze the situation, especially if he invokes the people in Fermilab, right? So any longer wavelength light, red for example, right, should be converted to white or blue. Makes no sense according to Bill's own model. Well, no, it's according to his interpretation of my model. Okay, let's find out what's wrong with this. This is the answer I give him. First, the electromagnetic rope leaving a prism does not get shorter, and it doesn't leave. Electromagnetic ropes extending from an atom at the edge of the prism relays, okay, the link length imparted by the frequency of the pumping atom. And as always, I like to illustrate so that there is no misinterpretation, okay? Here it is. If you have eyes, this is what you should see under the rope model, which is completely in concordance with what we see come in prism when we play around with prisms. I drew a white ball on the left-hand side because it's not so important. We're just saying white light comes in there, okay? And so I didn't have it pumping like in the case of red, yellow, and violet. But you can see that the red, yellow, and violet are pumping. The atoms are doing their quantum jump right at the edge of the prism. But you can see that the blue one, or the violet one, is pumping faster than the red one, and the yellow one is somewhere in between, which is in accordance with the rainbow, okay, that we should see coming out of prism. So what happens? You can see that way on the right, the wavelengths are different. The red one has longer wavelength, and the violet one has shorter wavelength, okay? So what's the difference between them? Well, the color has to do with wavelength. So we're consistent, and you can see there on the upper left-hand corner the wave equation, and you can see what's happening. When the rope has more links, which is like in the case of violet, each link is shorter. And when the links are longer, well, you have fewer links. That's it. That's what we're seeing there. And so, no, what you have is an atom like the red atom. It's pumping, and it's going to pump at a certain frequency, and that's the frequency it's going to send to the atoms down the road. In fact, to every atom in the room. It's going to send that light or that frequency to every atom in the room, which means every atom in the room is going to be stimulated by this atom in the same way. Okay, so no, the wave does not, the link, in other words, does not shorten when it comes out. It just, it's the atom which relays the signal to the following atom down the road. That's the mechanism. So please don't put words in my mouth. Make sure you, when you quote, you say that this is the way you think, not the way we think, that normal people think. This is the version that quantum essentially has. The wavelength flattened out in the direction of travel through the prism, and so you have white light coming in, and you should have white light coming out, because if quantum is correct and the wave goes back to its normal state after leaving the prism, because there are no atoms or electron waves holding it back, then we should see, you know, the wave going back to white light, and that's not what we observed. In other words, here I have comparison here. See, you can see that in this case you have the wave inside, or the waves plural, inside the prism. They break up, they disperse. Well, then if then when they come out they form a single, in other words, they no longer have an impediment like the electron waves inside the prism, then what should come out is white light. That's what should come out. And here we see the two, one against the other. Let's see if I put it up here. Okay, here you have them face to face. The one on the left is what we see in actual labs, and the one on the right is the one that quantum predicts. Essentially, is saying, oh, the waves that go through the prism are stopped by electron waves, or by whatever you want. I don't care what they want to put in there. But when they come out, they're no longer stopped, and light returns to its original speed. That's what they say. Well, if it returns its original speed, we should have white light out and not what we see on the left. So quantum has a big problem here, okay? Because their prediction does not come true. Okay, they're saying that the wavelength squashes inside a denser medium. When it exits the denser medium, light returns to its original speed, partly because, according to them, the wave never slowed down to begin with, because this guy talks about two waves, and then he says, oh, but they blend into one. First, he doesn't explain the mechanism. But assuming he explained the mechanism, he still has two waves, because the argument that quantum makes is that now when the light exits the prism, it no longer has the impediment that it had inside the prism. That means that when the light goes through the prism, it really goes always at the speed of it has in a vacuum, at 300,000 kilometers per second. Somehow, again, the mechanism is not there. Somehow, the electron waves slow it down, and then when that electron wave is not present when light comes out of the prism, light continues on its merry way at 300,000 kilometers per second. So aside from the fact that they do not explain the mechanism inside the prism, their prediction is that white light should come out of the prism, and that's not the case. So, quantum fails in every respect. And what I give you some homework. Go out there and look at the speed of light going into a glass or a prism or whatever, and you'll find all kinds of answers, all from PhDs. They've never figured it out, and they never will, because each one, no one can explain it with one-way mechanism. No one can explain it with particles or waves. And so, these go in one direction. The rope is a two-way mechanism, okay? Light goes both ways on a rope. Torsion goes both ways. Both atoms at both ends receive their signal at the same time, they both receive signals constantly, okay? Whereas in the case of one-way mechanisms such as particles and waves, it's just one way, and you got to wait, until the particle or the wave comes to you. And that creates lots of problems, especially when you're trying to explain, the difference in speed through glass. Okay. Let's see what I got here. Here you can see the picture that you can see the light already changes inside the prism. So light already disperses inside a prism. Okay, and when it comes out as a rainbow. So I just want to confirm that's exactly the case. Okay, none of this notion that white light comes out, but that's what quantum predicts. Okay, that white light should come out. Then we have also, like I said before, we have the issue of energy. Okay, and here quantum has a big contradiction. Okay, a big contradiction, because quantum says red light has a longer wavelength, yet travels faster through the prism. Okay, so red light travels faster, according to quantum mechanics, okay, than violet light, okay? And so we got a problem, because it turns out that red light has lower energy than violet light. Violet light, or ultraviolet light, compared to, the red light, I can't remember the word now, but violet light has higher frequency and therefore higher energy. But here they're insinuating the opposite. They're saying, look, red light has longer wavelength, but it travels faster through the prism, meaning that you would think, right, that what it is that it has higher energy. So, you keep that in mind, because I think they have another contradiction there as well. They have just one contradiction after another. Quantum has never resolved this issue, and this is a quantum issue. People want to say, well, this is classical. No, this is a quantum issue, because quantum claims that light is a wave. Photons also they use that word, meaning that it's a wave packet. They go back and forth. Here they use the particle, here they use the wave. What is a wave? Well, we don't know. It's just a waving of particles, I guess. So we don't know what a wave is. And when they explain this, they have these contradictions where light shortens because of the wavelength, because apparently the electron waves slow it down inside the medium. But then when it comes out, with all these, when it comes out of the prism, right? It comes out of, in the rainbow colors. And if there's no impediment, it should come back out white, according to their own prediction, right? So here's a summary. Let's go to the summary, because this is what you got to take with you. They have essentially three mechanisms. I only figured out two, because I can't consider what Fermilab does a mechanism. Hasn't explained anything as Bozo, Don Lincoln. Okay. One is the pinball mechanism. Think of the pinball machine. The little ball goes back and forth, just hitting all these atoms in this case, right? And light bounces off atoms, okay, and therefore travels a longer path because it zigzags, okay? So if light were to travel straight, it travels at 300,000 kilometers per second. Well, light can still travel at 300,000 kilometers per second, but if it goes back and forth in a zigzag, it travels a longer path, and therefore it goes slower than the one that goes straight. That's essentially the argument of the pinball mechanism. Well, quantum has rejected that, because obviously it's easy to debunk. One of them is that, the main one is that light would go in every direction if that were the case. In other words, you would not have focused light. Like, when you come out of a prism, you can see each one of the colors in a straight line going directly in front of it. that would not be the case. You would have this diffused light all over the place in every direction. So they got rid of the pinball mechanism. They realized that's not the solution. Then they came up with the absorption mechanism, because that is what quantum says. Then they throw it aside, like saying, well, no, that doesn't happen. But this is the way they explain other phenomena. They say that every atom absorbs light. So if you send light to an atom, the atom will absorb that light and re-emit it. That's what quantum says. That is quantum mechanics. And the absorption mechanism doesn't work for them when it comes to glass or a prism, okay? It says atom absorbs the photon or wave and re-emits it, but then light again would scatter. It would disperse radially in every direction. And so, they know they can't explain with the absorption mechanism. And then you have this idiotic Fermilab mechanism where amplitude is supposedly related to the slowdown of light. What this guy, Lincoln, explained is amplitude, and amplitude has nothing to do with speed. And don't take my word for it. Go to the site, go to this, look it up. What is it? Light Speed in Water by Fermilab, and you'll find it. And you'll find this guy giving this bozo presentation where he essentially explains amplitude. And amplitude has nothing to do with speed. So no, all three mechanisms fail for quantum mechanics. Quantum mechanics does not have an explanation. And second, if you go through the internet, you'll find all the PhDs, just each one with his own opinion. That's all they have. And all three opinions are irrational. And they know they cannot explain it with any of them separately. Okay? They cannot explain it. So in any of the above proposals, light should travel out of the prism at the original incoming speed. In other words, light should be white. That's the big problem with what's proposed by quantum mechanics. And in any of the above proposals, red light should have higher energy. Keep that in mind, because it travels faster than violet light. Actually, it's the other way around. Higher frequency equals higher energy. So you decide for yourself, if you're going to go with a particle or wave version of quantum mechanics, or you're going to go with a rational rope model. Because the rope model you can at least understand very quickly and very easily. There's no mystery to it, no fancy footwork, no concepts. We're saying there's an object, a physical object, which we call the electromagnetic rope that binds any two atoms. And the wave equation is straightforward. When frequency goes up, wavelength goes down, and here you have it. Here's the mechanism. When frequency goes up, the wavelength shortens. Okay? And when frequency goes down, you have low frequency, the wavelength, in other words, the link length, right, gets longer. It's very straightforward. And we don't have this problem of coming out of the prism and then turning into white light like quantum predicts. No, you have the rainbow because each atom at the edge of the prism is pumping. And it's pumping at the frequency that comes from the atom behind it. So there's an atom behind it, gives it a certain frequency, and this one relays that frequency to the one in front. So no, this guy said that maybe the way that the rope model predicts or proposes that the wave shrinks after coming out of the prism, that's not the case. What happens is the atom at the edge of the prism that's going to send light out of the prism is pumping at a given speed, and that's the frequency that it's going to send to the next atom down the road, which is an atom of air. So we have no problem with this at all. It's quantum that has to be has to try to explain what they do. And it'd be nice if they would illustrate their waves, how the wave of electrons interferes with a wave of light and somehow slows it down at the same time that when that wave of light no longer has the interference of the electron waves, it goes back to normal speed. Okay, they have to explain that mechanistically first. And second, even if that were the case, what should come out of a prism should be white light again. So that's my take on that today, and we'll see you on Sunday. I'll have to go with some of the other questions having to do with gravity. So please hold your breath until Sunday. We'll see you then. Don't catch the virus, by the way. Bye.